Modern theories tell us that there are 10 spatial or space-like dimensions to our reality. Hi, my name is Rob Bryanton. With this project, I have developed a creative way to use a variation of what's known as the point-line-plane postulate to visualize those 10 dimensions, a concept that most would have thought impossible for the human mind to comprehend. How can we do this? We start with a point. Like the point we know from geometry, it has no size, no dimension. It's just an imaginary idea that indicates a position in a system. A second point, then, can be used to indicate a different position, but it, too, is of indeterminate size. To create the first dimension, all we need is a line passing through any 2 points. A first-dimensional object has length only, no width or depth. If we now take our first-dimensional line and draw a second line crossing the first, we've entered the second dimension. The object we're representing now exists within a plane that has length and width, but no depth. Way back in 1884, a fellow named Edwin Abbott wrote a book about a race of two-dimensional creatures called Flatlanders. Whether these imaginary creatures could really exist or not, they're useful for thinking about what it would be like to live in a flat, two-dimensional world. If we were to watch a balloon passing through the Flatlanders' world, for instance, it would start as a tiny dot, become a hollow circle which inexplicably grows to a certain size, then shrinks back to a dot before popping out of existence. But what would the Flatlander actually see? Imagining the extremely limited viewpoint of a creature confined within this 2D plane gets even stranger than that. Now let's move to the third dimension. This should be the easiest for us because every moment of our lives, that's what we're in. A three-dimensional object has length, width, and depth. But here's another way to describe the third dimension. If we imagine an ant walking across a newspaper which is lying on a table, we can pretend that the ant is a Flatlander, walking along on a flat, two-dimensional newspaper world. If that paper is now folded in the middle, we create a way for our Flatlander ant to magically disappear from one position in his two-dimensional world and be instantly transported to another. We can imagine that we did this by taking a two-dimensional object and folding it through the dimension above, which is our third dimension. It'll be more useful for us as we begin to imagine the extra dimensions if we can think of the third dimension in this way. The third dimension is what you fold through to jump from one point to another in the dimension below. To be clear, no matter what dimension you are folding, it provides a way to move instantaneously from one distant position to another. A wormhole is the scientific term for this concept. Now let's look at the fourth dimension. Just like any other spatial dimension, it's made up of two opposing directions. But we 3D creatures only experience this dimension in one of those directions. Why is that? It's because you and I are made out of 3D atoms and molecules, and we derive our energy from chemical reactions which move in one direction only. But science shows us that time's reverse direction is just as valid, and in fact, the standard definition of antimatter is that it's matter which is moving backwards in time. So rather than saying the fourth dimension is time, let's use the word duration. If you were to imagine your body's duration as a shape in the fourth dimension, you could think of it as a long, undulating snake with your embryonic self at one end and your deceased self at the other. But because our reality is observed one quantum frame after another from the third dimension, we are like our second-dimensional Flatlanders. Just like that Flatlander who could only see cross-sections of objects from the dimension above, we as three-dimensional creatures can only see cross-sections of our fourth-dimensional self. And just as you and I require the fourth dimension to change from state to state, think about how for a 2D Flatlander, time would be one of the two possible directions in the third spatial dimension. Quantum mechanics tells us that the particles that make up our world are derived from waves of probability simply by the act of observation. It is for this reason that I like to refer to the fifth dimension as our probability space. And this relates very nicely to a theory which is now gaining acceptance. Advanced in 1957 by Hugh Everett III, his theory is commonly known as the many worlds interpretation of quantum mechanics. It was Everett who showed us that these parallel outcomes reside within a space which is orthogonal to spacetime, and the versions of the universe that we don't observe are just as real as the ones we do. What's orthogonal or at right angles to spacetime? With this project, this leads us to the conclusion that Everett's many worlds reside within the fifth dimension. One of the most intriguing aspects of this approach to visualizing each new dimension as being orthogonal to the previous one is that it means we can be observing one dimension and be unaware of our motion in an additional one. Here's a simple example. If we make a Mobius strip, take a long strip of paper, add one twist to it and tape the ends together, and draw a line down the length of it, our line will eventually be on both sides of the paper before it meets back with itself. It appears, somewhat amazingly, that the strip has only one side, so it must be a representation of a two-dimensional object. And this means that a two-dimensional flatlander traveling down the line we just drew would end up back where they started without ever feeling like they had left the second dimension. In reality, they would be looping and twisting in the third dimension, even though to them it felt like they were traveling in a straight line. The fourth dimension feels like a straight line to us, moving from the past to the future with what some have called the arrow of time. But that arrow is, without us even being aware of it, actually twisting and turning in the dimension above. So the long undulating snake that is us at any particular moment will feel like it is moving in a straight line in the fourth dimension, but there will actually be, in the fifth dimension, a multitude of paths that we can branch to at any given moment. Those branches will be influenced by our own choice, chance, and the actions of others. We move through those branches one Planck frame at a time, and this is why some physicists say that the fifth dimension is curled up at the Planck length, because from our reference frame, that's how it appears. It's important to note, though, that Everett was also very clear that causality could not be violated as we observe one outcome or another. So right now, there is zero probability that you or I can suddenly be in the world where, for instance, Michael Jackson is still alive. And yet the many worlds interpretation says those versions of the universe really exist within the quantum wave function. So how could we get there? We would need to fold our 5D probability space through the sixth dimension. I like to call the sixth dimension our universe's phase space. Why? A phase space is defined as a space in which all possible states of a system are represented, with each possible state of the system corresponding to one unique point in the phase space. So those points representing the versions of our universe where Michael Jackson is still alive are inaccessible to us from our current position within the fifth dimension, but they still exist within our sixth dimensional phase space. Now, as we enter the seventh dimension, we're about to imagine a line which treats our entire sixth-dimensional phase space as if it were a single point. You could say that this point represents what Einstein was thinking about when he said the separation between past, present, and future is only an illusion. Some would call this point infinity for our universe, all possible outcomes, all wrapped up as one single, timeless everything. So if we intend to draw a seventh dimensional line that passes through this point, we need to be able to imagine what a different point in the seventh dimension is going to be, because that's what our line needs to pass through. But how can there be anything more than infinity? The answer is there can be other completely different infinities, other different everythings, created through initial conditions which are different from our own Big Bang. Different initial conditions will create different universes, where the basic physical laws such as gravity or the speed of light are not the same as ours, and the resulting branching timelines from that universe's beginning to all of its possible endings will create a phase space of all possible states different than the phase space associated with our own universe. Think about this. What if the 7D line we just drew represented all possible universes with different values for gravity, with our universe someplace on that line? Lower gravity than ours would be in one direction, and higher gravity in the other. Would that line be a way to get to every possible universe? No. In order to represent other universes with the same value for gravity as ours, but with other basic physical constants changed, we need to branch off to the possibilities contained within the eighth dimensional phase space of all possible physical realities. And this would be true no matter what variables we were adjusting within the seventh dimensional line. We would still need the additional degree of freedom afforded by the eighth dimension to get to every possible physical universe. Now, how do we get to the ninth dimension? The same logical rules we've been using would apply. If we were to instantaneously jump from one eighth dimensional point to another without passing through the intermediate points, it would be because we were able to fold through the ninth dimension. Within this approach to visualizing the dimensions, then, the ninth spatial dimension is beyond any physical reality and is much more about information, a seething foam of possibilities which could represent impossible universes which exist only as concepts, or selection patterns which could be the beginning of a path toward a universe such as ours or any other. And to complete the logic we have used from the outset, we now take the entire ninth dimension and conceive of it as a single point. But this is where we hit a roadblock. If we're going to imagine the 10th dimension as continuing the cycle and being a line, then we're going to have to imagine a different point that we can draw that line to. But it can't be done. By the time we've imagined an ultimate ensemble of every conceivable information pattern as a single point of indeterminate size, there's no place left to go. M-theory says that our reality is defined from 10 spatial dimensions plus time. And that's what we're talking about here, a 10th dimension without time. As soon as anything tries to happen within the 10th dimension, we are spilled back into the dimensions below, as subsets are carved out from this ultimate ensemble, this omniverse, this timeless and unchanging everything which underlies our reality or any other. And that is a beautiful and fascinating idea for us all to ponder. I hope my project, Imagining the 10th Dimension, a new way of thinking about time and space, has given you some valuable food for thought, and that this will be the beginning of your exploration into understanding the underlying structures of our reality that the great scientists of our day are introducing us to. It's important to note that this project has reached millions of people around the world because it also could be related to many other belief systems, and not just mainstream science. I've created many other videos as part of this exploration of the wide-reaching implications of this visualization. Here's a list of some good starting points which look at each of the dimensions in more detail. You can also read more about these ideas in my blog or in my books, Imagining the 10th Dimension, O is for Omniverse, and Imagining the 5th Dimension. Thank you all for watching, and enjoy the journey. Imagining the 0th dimension. With imagining the 10th dimension, we start from a 0, which some would call a 0th dimension, and we move to the 1st, 2nd, and beyond using a repeating logical structure to eventually end up at a timeless, ultimate ensemble. When you get right down to it, that's what every respectable toe or theory of everything needs to describe. Some underlying thing that all else is derived from. Otherwise, you're back to the turtles all the way down joke that often comes up in these discussions. Reconciling this timeless everything, which with my project I'm calling the 10th dimension in its unobserved state, with the 0 that we start from, a point of indeterminate size, is the mind-blowing concept we arrive at with my project once we've imagined all 10 dimensions. I have often insisted that 0 is not a dimension because, after all, we need 2 new directions to travel within to define a spatial dimension. I have also suggested that the 0 and 10 represented on my Helix logo for this project are shown to be on a line within the other dimensions because they represent the 2 directions which take us towards the infinitely large one way and the infinitesimally small the other. Connecting 0 to 10 is the most recent entry where we've talked about that idea. But consider this, even if we ignore everything but this 0, this point of indeterminate size, we should remember what this means. Even though we tend to think of this point as having no size, the definition of indeterminate is really all possible values are true. Incredibly, that means that this lowly point that we start from does have a way that we can think of it as being infinitely large, encompassing absolutely everything within the information that becomes reality. So with that in mind, and for the sake of discussion here, let's continue to pursue this idea that there could be a zeroth dimension. We began this entry with a quote from Charles Seif's Zero, the Biography of a Dangerous Idea, a book which discusses the relatively recent origin of this most powerful of numbers. Why does Seif call zero a dangerous idea? As an example, his preamble chapter includes an anecdote about a billion-dollar warship that was suddenly dead in the water when a software bug resulted in a divide by zero error which completely crashed the computers running the ship. Then chapter 1 begins with these thoughts. As natural as zero seems to us today, for ancient people zero was a foreign and frightening idea. An Eastern concept born in the Fertile Crescent a few centuries before the birth of Christ, zero not only evoked images of a primal void, it also had dangerous mathematical properties. With zero, there is the power to shatter the framework of logic. The beginnings of mathematical thought were found in the desire to count sheep and in the need to keep track of property and of the passage of time. None of these tasks requires zero. Civilizations functioned perfectly well for millennia before its discovery. Indeed, zero was so abhorrent to some cultures that they chose to live without it. Gavin Gyorbrand, author of the brilliant Everything Forever, Learning to See Timelessness, liked to point out that some cosmologists say the accelerating expansion of the universe will eventually take us to an absolute zero of perfectly flat space, an empty and formless void which seems like the most grim future imaginable. Gavin's take on this idea was that this zero we're headed towards is not empty, but full of all the other possible states, and this can be supported by the commonly held viewpoint that our universe arises from the breaking of an underlying symmetry. This means that our universe is now headed back towards a natural return to the perfectly balanced whole that exists both before and after the existence of our universe. Here's a quote from chapter 20 of Gavin's book. 1 plus negative 1, plus 2 plus negative 2, plus 3 plus negative 3, plus and so on, equals 0 plus 0 plus 0 plus and so on, which equals 0. The simplest, most straightforward way of summing all numbers is to sum the equal but opposite numbers together as shown here. So for a moment, we will imagine that the correct sum of all numbers does sum up to and equal 0. Except this means that we need to change the value of 0 away from being no things. We need to treat 0 as the largest value in the mathematical system, which actually includes the two already vast infinities of positive and negative numbers. Suddenly, 0 has become an infinite whole that contains all other numbers. Every positive and every negative number on the real number plane is summing or combining together to form an ultimate number of absolute value. Obviously, this is not math as we know it. This is a math without time, without process, a math of truly infinite values. So we have made a dramatic change, and the next step is to see the effect that changing the value of 0 has had on the value of other numbers. If we are going about this bravely, as we are imaginatively exploring a series of ideas, and so the brain is actually working, we notice that the values of other numbers have also changed, transformed in the same shift that we have taken with 0. Ordinarily, the nothing of 0 is a foundational axiom. Our foundation is shifted dramatically. What now is the value of 1 or 2? If 0 is seen to contain all other numbers, then logically all other numbers must have a lesser value than that of 0. If 0 is the largest value, the only way there can be lesser values is if we remove some measure of value from the whole of 0. For example, suppose that we take away a negative 1 from 0. What remains in the absence of that negative 1? 0 is still very large, but 0 is no longer an absolute value containing all other numbers. Something has been removed from it. But what value does 0 transform into to show that loss? The answer is simply that 0 minus negative 1 equals 1. The missing negative 1 causes 0 to transform into the value 1. If 0 contains all numbers within it, and we take away a value, 0 then contains all numbers except the removed value. So it is still a very large number like 0, but it is no longer the complete whole of all numbers. It is 1, a very large number 1. So if we treat what just happened as the logical rule, we can now discover the values of other numbers in this system. For example, the number 2 is the sum of all numbers except -2 is missing. So it is also near 0, but its content is less than 0 and less than 1. The number 3 contains all other numbers except -3. So it is very large, but smaller than 2, 1, and 0, and so on and so on. The transformation that has happened is not simply an inverse reversal of ordinary mathematics. Rather, in this mathematical system, the value of a number decreases as we count towards greater numbers, since more of the negative numbers are being removed and placed somewhere else. Now, I should point out, just for the sake of clarity, that switching to the negative, the number -1, is a combination of all numbers except that a positive one is removed, which would otherwise create the balance of 0. And in removing a positive 2, the whole shows that loss by becoming the number -2. Unlike ordinary math, where negative values are less than nothing at all, here the numbers -1 and -2 are very large. In fact, the content of -1 is equal but inverse to the content of +1. In physics, matter and antimatter particles are equally substantive, yet inverse in form and structure. Do you follow Gavin's logic here? Saying that 0 minus -1 equals 1 really makes perfect sense in ordinary math. But framing this idea in terms of 0 being full and any of the other numbers as being slightly less than that requires a powerful mental shift. This shift takes us to an understanding that the broken symmetry that creates our universe or any other is defined by what's missing from it. In the case of our own universe, we know there is much less antimatter than would be expected if our universe is derived from an underlying symmetry state. So it is this absence of antimatter which is one of the defining factors that resulted in our particular universe. There's no question in my mind, Gavin Gurbrand was a genius, and I'm sad that he's no longer with us. And P.S., I really should remind everyone that Gavin's book is available in hardcover, softcover, or as a downloadable PDF from 10thdimension.com/store. Next time, we'll look at a simple idea that has powerful implications, imagining the first dimension. My name is Rob Bryanton. Enjoy the journey. Imagining the first dimension. The first dimension is a line passing through 2 points. Is there anything simpler? But within this discussion of the dimensions that make up our reality, the power of the line is important to keep in mind. This line has length only, no width or depth. Right at this instant, we could define a point at the tip of my nose and another at the tip of your nose and visualize a line that passes through those 2 points. Even though that line most likely passes through the Earth's crust to get from my position on the planet to yours, that means little to the one-dimensional line we have just drawn. And as you and I go about our day, that line will move around, continuing to pass through those 2 points we defined. Billions of light years away, if we were to follow that line, it would be passing through one galaxy after another as you and I change our positions relative to each other back here on Earth. And the Earth itself turns on its axis and orbits around the Sun, and the galaxies move through space. But ultimately, at any one instant, we are still just talking about a simple one-dimensional line. So no matter what dimensions we're thinking about, there will always be a point that we can define that represents the entirety of a dimension in a certain state, and a second point representing that dimension in a different state, and there can be a one-dimensional line that passes through those 2 points. But what that line passes through to get from one point to the other, and what that line extends to as it passes beyond each of those points, can be a mind-boggling realm of information and different forms of reality. That's the simple power of the line. Traveling from one point to another is a way of thinking about time for any dimension, since time is a way of describing change from state to state. While we, as creatures made out of 3D atoms and molecules, perceive the line that gets us from one state to another as being in the fourth dimension, that concept works equally well for any dimension, which is why with this project we say that time, for an imaginary two-dimensional creature, would be one of the two possible directions in the third dimension, and so on. In imagining the zeroth dimension, we talked about how our universe or any other arises from a breaking of symmetry, and how the original animation that started this project visualizes the dimensions by starting with a point of indeterminate size and moving through the first, second, and so on with repeating logical steps. This process also works from the other end. We can start with the 10th dimension as a point of indeterminate size, then imagine the descending steps from the 9th, 8th, and 7th dimension to represent an increasingly finely detailed paring away of the possibilities represented in the 10th dimension as a timeless set of all possible states, or an ultimate ensemble of all possible information patterns conceived of as a single, unchanging entity. Thinking then of the point that represents our universe locked in at the 7th dimension, and thinking of a point in any other dimension allows us to think about all the one-dimensional lines that could exist within or be connected to our universe, and how all those lines still represent only a tiny subset of the potential contained within the 10th dimension. Finally, in imagining the second dimension, we talk about how this one-dimensional line we're portraying has caused some people to say, that's impossible. Something with no width or depth can't exist. If you're one of those people, this will be a good next entry for you to watch. Till then, enjoy the journey. Imagining the second dimension. Let's go back to basics. The most important thing to remember as we're talking about these 10 dimensions is that they're spatial dimensions. Some people get confused by that word, spatial, because they think it's intended to only apply to the third dimension, the length, width, and depth of the space we see around us. In fact, some physicists do prefer to use the term space-like when talking about the extra dimensions. No question, when you take a three-dimensional space and add an additional right angle to it, you are entering a realm which is difficult for us to picture, and it certainly behaves in ways that are beyond the limitations of 3D space. That's what imagining the 10th dimension is all about. Likewise, some people have difficulty with discussing the first and second dimension. How can something with no depth even exist, they ask. It is a bit of a mind bender. We start with a point that has no size and no dimension. We make a second point someplace else, and the line that passes through those points is a representation of the first dimension. If you can imagine a third point that isn't on the line you've just created, you have a way of thinking about the second dimension. A line passing through this new point and the old line defines a plane. But if the lines you're thinking about are like pencil lines, which already have a length, width, and depth, then you're really not visualizing the right thing. Do you know what I mean by that? If I say, imagine you're on a boat in the middle of the ocean, and you say, I don't own a boat and I hate the water, what does that prove? The concept of boats and oceans doesn't change whether you're willing to imagine them or not. Likewise, if I say, imagine something that has length and width and no depth, and you say, I refuse to imagine that because something that has no depth can't exist, where have we gotten? Nowhere. But does refusing to discuss an idea mean the idea doesn't exist? Of course not. We can have a perfectly good discussion about dragons which don't appear to exist in our world because dragons are an idea which we are capable of describing and thinking about. Same goes for the second dimension. It's not part of our 3D world, it's something separate, but it's still something we can think about and talk about. In What Would a Flatlander Really See, we looked at the imaginary 2D creatures invented by Edwin Abbott for a book he published way back in 1884. Flatland, a romance of many dimensions. Could Flatlanders really exist? Perhaps no more than dragons, but we can have a perfectly good discussion about the idea of Flatlanders and what it would be like to live in a world that has length and width but no depth. What would it be like to look around you within that world, where all you can make out is lines all within the same plane? That is a mind-bending exercise, good food for thought, regardless of whether it would really be possible for some kind of awareness to exist within such a ridiculously limited frame of reference or not. Over the next 9 entries, we're going to look at each of the dimensions from the 2nd all the way up to the 10th and see what kind of a mental castle we can build for ourselves, one brick at a time. Along the way, I want you to keep reminding yourself about something called the point, line, plane postulate, which uses the same kind of logic as the line, branch, fold of the Imagining the 10th Dimension project. This postulate is the accepted method used to imagine any number of spatial dimensions using the same repeating pattern. 0, a point. Whatever spatial dimension you're currently thinking about, imagine a geometric point within that dimension. Remember, when we say that this point has no size, what we really mean is that this point's size is indeterminate. Indeterminate means that any and all sizes you care to imagine, from the infinitely large to the infinitesimally small, are true for that point. Let's say that this is a point within dimension x. 1. A line. From the current dimension you're examining, find another point not within that dimension. An easy way to do that is to imagine the first point at its largest possible size within the constraints of its own dimension, and then ask where a different point would be that isn't encompassed by that first point in its infinitely large state. Once you've found a second point, draw a line through both points, and now call what you're looking at dimension x plus 1. 2. A plane. Again, think of both of those points encompassing their largest possible version within the constraints of the current dimension, and find a point that isn't part of what those 2 points are encompassing. Now you're thinking about dimension x plus 2. This logic can start from any spatial dimension, and it can be repeated infinitely. That is, once you've imagined dimension x plus 2, you can rename it dimension x and repeat the pattern as many times as you want. Here's an important thing to remember. If we're not assigning any meaning to the dimensions we're visualizing, there's no reason to stop at 10. However, with this project, by the time we've arrived at the 10th dimension, we do find a way to say that we have arrived at the most all-encompassing version of the information that becomes reality, or the underlying symmetry state from which our universe or any other patterns emerge from the breaking of that symmetry. And I do hope you'll enjoy the journey as we work our way through this logical presentation, one step after another. Imagining the third dimension. Some people dismiss discussions of the second dimension, saying it would be impossible to see something with no depth. What if I told you the third dimension is also impossible for us to see? In my original Imagining the 10th Dimension animation, I said that imagining the third dimension should be the easiest for us, since that's what we see around us every day. But there is a problem here. Most of us, when we imagine the third dimension, also imagine energy, change, and life itself as being in the third dimension. But how can any of these processes be part of the third dimension when what we're talking about is space without time? In the remarkable television series Through the Wormhole with Morgan Freeman, physicist Julian Barber says this: "In my view of the universe, it's just like a huge collection of snapshots which are immensely richly structured. They're not in any communication with each other. They're worlds unto themselves. In some very deep sense, the universe, a quantum universe, is static. Nothing changes. What Dr. Barber is conveying here is that our 3D universe is like a giant flip book animation, and even though it feels to us like our observed reality is continuous, each of those snapshots he's referring to represents a frame of 3D space without time. Each of those frames is defined by the speed of light and Planck's constant, which is the smallest possible distance that can be observed, and the smallest possible duration that our reality can have before words like distance and duration lose their meaning. So the only way for change to occur is to string those snapshots together and view them from the fourth dimension, one Planck frame after another. There's a second problem with the way people tend to think about the third dimension. It's so easy to forget that it takes time for light to travel to our eyes. So even if we look at our own hands, there was already a tiny delay for the time it took for the light rays to bounce off our hands and arrive at our retinas. If we're trying to imagine the third dimension then as space without time, we're already imagining something that can't be seen. This is easier to think about when we move out to the vast distances of the nearby stars. If I'm looking in the night sky at a star that's 10 light years away, I'm looking at what that star looked like 10 years ago. I'm not looking into space, I'm looking into space-time. And right next to that star could be a different one that's 20 light years away. There those two stars are, seemingly side by side, and yet when I'm looking at one, I'm looking 10 years into the past, and when I'm looking at the other, I'm looking 20 years into the past. Isn't it amazing to think about how all the different distances of galaxies, stars, planets, and satellites that we might see through a telescope blend together into a vision not of 3D space, but of 4D space-time? And even though it's on a much smaller scale, the same is true if we look at our hands, then look at some other object that's further away. Even though our brains tell us we're looking at a 3D world, the time it takes for light to reach our eyes from any particular object will be defined by how far away that object is from our eye. And what we're seeing at any particular instant is really a blend of those tiny delays, a snapshot of 4D space-time. The next time someone tells you that the first and second dimension don't exist because something with no depth is impossible, think about how the third dimension has the same problem. In our minds, we can visualize objects that are constructed from length, width, and depth, but we can't actually see them with our eyes unless they have duration within 4D space-time. Does that mean the third dimension doesn't exist? Of course not. But those 3D snapshots of space without time are much stranger than our intuition might tell us, because within each of those snapshots lies the potential for quantum entanglement, which can occur at any distance across the universe. Remember, those connections and superpositions are not just faster than light, they're instantaneous. As Julian Barber says, a frame of the quantum universe exists in a place where time doesn't exist. And if that idea seems unimaginably strange to us, perhaps that's because it's so easy for us to forget that you and I are really part of something larger than the third dimension. Imagining the fourth dimension. Here's where we start getting into some possible confusion because the same word can have many different meanings. When people say that time is the fourth dimension, what does that mean? The fourth dimension adds a way for the third dimension to change. This is obvious when we say the third dimension is space without time. But the entropy-driven arrow of time that people associate with this concept is obviously not spatial because it behaves in ways that are different from the first three dimensions. This is why some people prefer to say that the fourth dimension is a temporal dimension, while the first three are spatial. But the more we learn about space-time and general relativity, the more we realize that time is not just an arrow. The fourth dimension stretches, it bends, and quantum entanglement shows that it's possible for particles to make instantaneous connections within it, even for there to be causality in time's reverse direction. And as mind-blowing as this may be to fathom, the accepted definition for antimatter is that it's matter which is moving backwards in time. This is why, with this project, I prefer to call the fourth dimension duration. I ask people to accept that time is a direction, not a dimension, in the same way that up or forward are directions rather than dimensions. Two opposing directions can be used to describe a spatial dimension, and time and anti-time are two words we can use to describe the fourth dimension. But they're not the only words, and this is important because all we're really trying to do here is come up with words that describe the dimension which is at right angles to the third dimension. Here's something important to remember. None of these dimensions exist in isolation. You can't make a 1D line without using points. You can't make a 2D plane without lines. You can't make a 3D space without planes. And you can't have a 4D duration without multiple Planck frames of space. Saying the fourth dimension is duration makes no more sense than saying the third dimension is depth, if when we say those phrases, we're thinking you can have duration without space, or depth without length and width. Saying the fourth dimension is space-time, then, at least acknowledges that the fourth dimension encompasses the dimensions from which it is constructed, and doesn't exist in isolation from the other dimensions. Let me say this again. It doesn't matter what label you put on the fourth dimension, or any additional dimension, as long as you're thinking about how the new dimension is somehow at right angles to the ones before. A rose by any other name still smells as sweet, to paraphrase Mr. Shakespeare. So, time is not really a dimension, but no matter what dimension you're examining, the direction of time is a word we can use for tracking change from state to state. In Aren't There Really 11 Dimensions, I insist that it makes no sense to say that the first three dimensions are spatial, and the fifth dimension and above are spatial or, at very least, space-like, but then to say that the fourth dimension isn't spatial. If that were the case, then the mental castle we're building here has a very rickety layer at the fourth dimension, and the whole structure is prone to crashing down. Last entry, we talked about how it's really impossible for us to see the third dimension because it takes a certain amount of time for the light from anything in the third dimension to reach our eye. And that's just as true for our hand in front of our face as it is for a star 10 light years away. Saying that a third-dimensional object has length, width, and depth is a phrase we casually say, but we have to keep in mind that discussing a third-dimensional object like a cube is the same as discussing dragons or flatlanders. A 3D cube is an idea which we can freely discuss, but without using the fourth dimension to view such an object, it's only a concept. Likewise, persons who talk about tesseracts as being four-dimensional objects say that this is what the real fourth dimension is like. But what we're really talking about with a tesseract or any other n-dimensional shape is the same as a cube. It's an idea. In order for a tesseract to really exist, it has to have a duration within its dimension. And when we watch an animation of a rotating tesseract, we are visualizing how that structure could rotate and change from state to state over time when viewed from the third dimension. Likewise, just as a cube represents a simple and idealized shape within the third dimension, but there are the limitless range of other shapes that can exist within the third dimension, the additional degree of freedom afforded by the fourth spatial dimension allows for an even larger number of other shapes which can exist within that dimension. One word physicists use to describe the path an object takes within space-time is a world line. Another word for a fourth-dimensional shape, coined by author and futurist Bruce Sterling, is a spime. With my Imagining the 10th Dimension project, I ask people to visualize themselves in the fourth dimension as a long, undulating snake, which is a way to think about the data set that represents a person's length or duration within the fourth dimension, from conception to death. Do you see how that snake is a spime? Depending upon your point of view, though, that snake could be much blurrier than what we show in the original animation. Every day, our bodies are exchanging atoms with the outside world through the air we breathe, the food we eat, and the water we drink. A constant cycle of repairs and replacement means the spine representing a person from conception to death is a much more wide-ranging and interconnected shape than what we might first imagine. One of the 26 songs attached to this project, called Change and Renewal, is about this idea. Let's finish off by thinking about the point-line-plane postulate again, which can be used to visualize any number of spatial dimensions. The trick I've suggested you start with each time is to think of a point that encompasses the entire dimension, then find a point that is outside of what that first point encompasses. So a one-dimensional point, in the largest version of its indeterminate state, occupies the entire length of a line, and some new point not found anywhere on that line allows us to visualize the second dimension. A two-dimensional point, in its largest version, fills an entire plane, and a point not within that plane gets us to the third dimension. A third-dimensional point, at its largest version, is like a single Planck unit-sized slice of the entire universe, and allows us to think about the possibility that Julian Barber has pointed out, that each of those 3D frames allows for the instantaneous quantum connections often deemed as supremely mysterious and unfathomable. Having said that, though, we still have to decode the mystery of how we can have a physical world made out of objects that are not infinitely large within the third dimension. And this is why I say those quantum connections are at right angles to space-time. So let's continue the point-line-plane postulate's logic into the fourth dimension. A 4D point at its largest version would encompass the universe not just in space, but in space-time. The point would reach from the beginning to the end of the universe in the same way that a photon traveling at the speed of light would perceive itself to be simultaneously emitted from a distant star and arriving at an observer's retina. This is an important concept we looked at in Light Has No Speed. It also ties nicely to something Einstein said a number of times. There is a way of thinking about reality in which the separation between past, present, and future is only a stubbornly persistent illusion. What's outside that largest possible 4D point we've just imagined? Well, if you are a person who has been trained to believe that free will is also nothing more than a stubbornly persistent illusion, you might well say, that's as far as we need to go. After all, if the universe was set in motion at the Big Bang, and anything we do is an inevitable outcome based on what has come before, then the largest 4D point we can imagine accounts for all of that, from the beginning to the end, including the now that each of us is observing at this very instant. But what if you believe in free will? With this project, that's where we start to think about the fifth dimension. Imagining the fifth dimension. We keep returning to this idea. Every time we add a spatial dimension, we need to find a way to think about how the new dimension is at right angles to the ones that have come before. Another word for this concept is that each new dimension is orthogonal to the previous ones. Last entry we looked at how it makes the most sense to say that the fourth dimension is space-time, a dimension which enfolds length, width, depth, and duration, and to accept that the fourth dimension is spatial. Yes, as creatures who get their energy from chemical processes that obey the thermodynamic laws of entropy, we appear to be moving in only one direction within that dimension, a direction which we call time. But the evidence is strong that the opposite direction, anti-time, is just as valid and just as real. And having two opposing directions is one of the basic attributes added by any additional spatial dimension. So what's at right angles to space-time? It's interesting to read this quote from a lecture by Stephen Hawking. One can think of ordinary, real time as a horizontal line. On the left, one has the past, and on the right, the future. But there's another kind of time in the vertical direction. This is called imaginary time, because it is not the kind of time we normally experience. But in a sense, it is just as real as what we call real time. And it's interesting to think about this. One of the central ideas to this project's approach to visualizing the extra dimensions is Everett's many worlds interpretation of quantum mechanics, which explains how every possible outcome for our universe is equally real, but as observers we can only see one of those universes at a time. According to Everett's theory of the universal wave function, the reason we can't see any of the other universes is because they exist within a subspace which is orthogonal to the ones we are observing at any particular instant. But even though Hawking has talked about another kind of time which is at right angles to our space-time, and Everett has talked about the other parallel universes being orthogonal or at right angles to the version of the universe any one of us is observing right now, neither of them have said that these additional realms are in the fifth dimension. Why is that? Is this a failure of imagination from two of the most brilliant minds of the 20th century? Or is this a free will discussion? This is where my project's line branch fold concept for imagining dimensions becomes particularly useful. The fifth dimension, by virtue of being at right angles to all of the dimensions that have come before, gives us a way to get to those other connections of the quantum world and Everett's many worlds that might seem unimaginable from the viewpoint of someone who believes there's nothing more than 4D space-time. In 2007, a team of scientists at Oxford under the direction of David Deutsch published a new proof equating Everett's many worlds interpretation with the probabilistic outcomes at the quantum level and the parallel universes resulting from chance and choice. And New Scientist magazine declared this to be one of the top science news stories of the year. In 2010, a team of scientists at Oxford participated in a speculative art project created by John Ardern and Anab Jain as Superflux, the fifth-dimensional camera project. David Deutsch acted as one of the consultants on this project too, but of particular note is a video they created featuring Dr. Simon Benjamin, who is from the Quantum Information Processing Interdisciplinary Research Collaboration, the QIPIRC, based at Oxford University. Within this video, you'll see Dr. Benjamin show a diagram very similar to the ones from my project of branching timelines resulting from chance and choice, and he suggests that these are occurring at the fifth dimension. Einstein, another of the great minds of the 20th century, accepted the existence of the fifth dimension. He did take a while to get used to the idea, but in 1923, he eventually gave his approval to Theodore Kaluza's proposal that the field equations for gravity and light are resolved for our space-time when they're calculated at the fifth dimension. The fifth dimension then becomes a way to combine Einstein's theory of general relativity with Maxwell's equations describing electromagnetism. A few years later, with Oscar Klein's additional input, the resulting Kaluza-Klein theory would eventually become the starting point for string theory. But if we're talking about something that is at right angles to space-time, why can't we see it? Well, we've already talked about our mythical 2D flatlanders who would be unable to perceive up and down because it was outside of the length and width of their 2D world. And we've also discussed that although we've been taught that the world around us is 3D, the startling fact is that the time it takes for light to travel to our eye means it's impossible for us to see the third dimension by itself. So asking why we can't see the fifth dimension may be like asking why we can't see the other side of a building as we stand in the middle of a street. It's not that the back of the building isn't there, or that it's impossible to see, it's just that we can't see it from our current reference frame. But the standard explanation for why we can't see the fifth dimension and beyond is because it's compactified or curled up at the Planck length. Since we've already established that our 4D space-time is not continuous, but is divided into 3D frames or quanta, I have proposed that it follows that our physical window into the fifth dimension is only one Planck frame wide, and the various aspects of our awareness can, as we saw in our opening quote from Winston Churchill, connect into the fifth dimension more fully. Make no mistake about it. With this project, I am insisting that we are really not in the third dimension, or even the fourth dimension. Our now is a moving point within a fifth dimensional probability space, And I believe the more that people embrace this idea, the deeper their understanding of our reality will become. The analogy often used in string theory is to think of the fifth dimension as being like a garden hose stretched out on the ground. From a distance, the hose looks like a line. But up close, we can see that the walls of the hose are curled up on themselves, so that if an ant were to walk inside that hose, it could go from one end to the other, the straight line of the fourth dimension, but be moving in a second dimension as well as the first. In my Imagining the 10th Dimension animation, I showed a Mobius strip and asked people to think about how a flatlander moving on this strip would feel like they were traveling in a straight line, but in reality they would be twisting and turning in the dimension above. This is useful as a way to think about the fifth dimension, but the garden hose analogy adds one further wrinkle. What if a fly were to enter our hose? Unlike the ant, the fly would be able to travel not just in a second dimension, but a third. So if our hose were 4D space-time, the ant would be moving in the fifth dimension, and the fly would be moving in the sixth. You and I, it appears, are ants rather than flies. But next entry we'll talk about how that's a good thing, as we move on to imagining the sixth dimension. Before we finish, though, I want to mention one final thing. I was thrilled to read recently that well-known physicists Leonard Susskind and Raphael Bousso have published a proof equating the branching probabilistic outcomes of Everett's many worlds with the string theory multiverse. I'd like to give you a link to Sean Carroll's blog entry about the new proof, and also here's a link that was published at archive.org. And while we're looking at links, here's a Discovery Channel blog entry about a new theory analyzing black holes from the perspective of the compactified fifth dimension we've been talking about in today's entry. Imagining the sixth dimension. What's the difference between the fifth dimension and the sixth dimension? With this approach to visualizing the dimensions, that question comes up a lot. After all, if the fifth dimension includes every possible state for the universe which can be connected to the now any one of us are currently observing, why do we need to talk about anything beyond that? Let's pull out a piece of paper and ponder this question further. First of all, put a dot near one edge of the paper and label it the Big Bang. Likewise, place a dot near some other edge of the paper and label it the end of the universe. Finally, draw a line that passes through those 2 points and place a point somewhere near the middle of that line, which we'll label U. Okay, if that middle point represents U right now, then let's place another point nearby, but not on the line we've just drawn. Do you see how this point could represent some other version of you, such as the one where a childhood accident completely changed your life? Or even just the version of you that got bored with this entry and stopped watching 10 seconds ago? There could be a new line which extends from the Big Bang and passes through this alternate version of you, and each of those could be thought of as a one-dimensional line. But the only way the line for version 1 and the line for version 2 could be considered simultaneously is if we were to consider the 2D plane of that paper we were drawing on. In fact, we could place another point earlier on one of the lines and say that it represents your moment of conception, and then imagine an array of possible lines representing all of the versions of you that could possibly have existed from your moment of conception onwards, and they could all be contained within this 2D plane. Now let's think of a different point, but in this case let's imagine that it's floating a few inches above the paper. Perhaps this new point represents the version of the universe where dinosaurs never became extinct, which would mean that you, as we know you, wouldn't even exist on that line. We can imagine a one-dimensional line that passes through the Big Bang point on the paper and this new point. We can imagine a different 2D plane that passes through our first or second line and this new dinosaurs line. But here's something important about what we've been visualizing. The only way we consider all three lines at the same time is by using the third dimension. I hope it's obvious by now that the point-line-plane postulate tells us the logic we've just used to think about the first, second, and third dimension is directly translatable to the fourth, fifth, and sixth, which means that with a piece of paper and a bit of imagination, we've already visualized the first 6 dimensions of our reality. But wait, some of you might be thinking, wasn't it arbitrary for me to place the dinosaurs line outside the plane of my paper? Couldn't I just have easily placed a point at the center of the paper, called it the Big Bang, then imagined that all around the outside edge of the paper were points representing all the different universes that could have resulted from the initial conditions that created our unique universe with its locked-in fine structure constant? And you may be surprised to hear that I'm willing to agree with that statement. From the initial conditions of our universe, we can get to any of the possible universes which the many worlds interpretation tells us really exist, just as real as the one we're observing. From anywhere else beyond the Big Bang, though, we're already seeing a paring away of possibilities. When one version of the universe is observed, the other universes are not. And causality shows us that this renders some of those other universes permanently inaccessible from that point forward on our entropy-driven line of time. How would you or I get to the universe where it's this point in time, which we call the 21st century, but dinosaurs never became extinct? Everett's theory tells us that a version of the universe must exist where dinosaurs are living and dying right now, and those dinosaurs are observing all the different versions of the universe where they still exist. So why can't you or I get there from here? In other words, if everything is probabilistic outcomes, why does it appear that there is zero possibility that the next possible now for us might include this dinosaurs world line? The answer is there is a missing degree of freedom. If you and I were within the 6th dimension rather than the 5th, then we would be able to leap across those different world lines and get to those other versions of the universe which are not causally connected to the one we're in right now. And as we said last time, this is because you and I are ants, not flies. Every instant that we observe is one Planck frame beyond the instant before, which gives us the impression that the 5th dimension is compactified, or curled up on itself. If the 4th dimension is like the straight line of a garden hose stretched out on the ground, the 5th dimension is like an ant walking inside that hose, while a fly inside that hose would be able to flip from one location to another without having to worry about 5th dimensional causality. What we're talking about with the 6th dimension, then, is the phase space of the set of parallel universes resulting from our universe's unique initial conditions. A phase space, to quote Wikipedia, is a space in which all possible states of a system are represented, with each possible state of the system corresponding to one unique point in the phase space. Let's sum all this up. Everett's many worlds interpretation says there is a wave function which encompasses every possible state for our universe, and I'm saying that's the 6th dimension. But because we're in the 5th dimension, choosing from a set of causally related outcomes that are available to us one Planck frame after another, there are versions of the universe which have nothing to do with us, like the version where I died in a car crash yesterday, or the version where dinosaurs never became extinct. Likewise, the version where I decided to rob a bank yesterday must exist, but with my free will I chose not to observe that universe. All of those other universes have nothing to do with the universe I'm observing, even though I can acknowledge their existence within the 6th dimension. So, what's outside our phase space? Thinking back to that piece of paper we started from, there are a few other ideas we can glean from this. First of all, that first and second point we drew, representing the beginning and end of the universe, can be joined with a line. But more properly, What we're talking about then is a line segment. A true line would pass through those 2 points and extend past the edge of our paper and out towards infinity in either direction. This gives us a way to think about how both before and after our universe is the same thing, a return to an underlying state which is outside the system representing all possible versions of our unique universe. But wait, there's that word again, system. In my original animation, I described the point we start from as being something that indicates a position within a system. As we just saw, a phase space includes all possible versions of a system, with each possible state of the system corresponding to one unique point within the phase space. So we can extend our analogy here to think of our paper as being on an endless landscape covered with other papers, none of them touching, many of them widely separated from each other, each of them representing other universes or systems with other initial conditions and basic physical laws. The multiverse landscape. And within some of those other systems would be creatures sufficiently advanced to be able to look around and wonder how they ended up in a universe where the laws of physics appear to have been uniquely fine-tuned in a way to allow their universe to exist. This idea is known as the anthropic principle. As I say in my song, The Anthropic Viewpoint,
if there's other worlds and we've just missed them, no way to know what's outside our system. We're like goldfish living in a bowl. What's beyond that we can never know? All we can do is theorize, 'cause we can never get outside. In the anthropic viewpoint, the reason we're here is because we're here. And if it were impossible, then we wouldn't be.
Coincidentally, as we talk about the sixth dimension, it's interesting to note that cosmologist Martin Rees has told us only 6 basic physical constants need to be defined to create our unique universe. Check out his book, Just 6 Numbers, The Deep Forces That Shape the Universe, for more about these concepts. It's also interesting to note that string theory predicts there could be 10 to the power of 500 other universes out there in the multiverse landscape, each with its own unique physical laws. So we can't get to those other universes, those other systems, from the 6th-dimensional phase space representing our universe. Why not? Because we haven't achieved that degree of freedom yet within our approach to visualizing the dimensions, which of course will lead us to our next entry, imagining the 7th dimension. Imagining the 7th dimension. A point represents a position within a system, and as we add dimensions, the system becomes more complex. In the Imagining the 10th Dimension animation, we're asked to think of our universe with its locked-in fine structure constant as a point at a position within the system of the 7th dimension, which means some other 7-dimensional point would be a way to get to some other universe with different basic physical laws than our own. Just how out there is this idea? Some string theorists have said that there are 10 to the power of 500 other universes out there, in something we can call the string theory landscape. Other cosmologists have suggested that the number of other possible universes out there approaches infinity, and that we are just in a tiny sliver of something called the multiverse. Either way, what we're trying to visualize here is a position within that landscape, and within that position we would find a way to get to Everett's universal wave function representing all possible outcomes for our particular universe. Here's a graphic which was part of a great article published in November 2007's Scientific American, written by Cliff Burgess and Fernando Quevedo. The article is called The Great Cosmic Roller Coaster Ride. The text that accompanied this graphic said this: according to string theory, our observable universe is a small part of a larger space having more dimensions than the 3 we directly see. The other dimensions may be microscopic in size or otherwise difficult to penetrate and crumpled up in a funky shape known as a Calabi-Yau space. The observable universe may be on a membrane, or simply a brain, sitting at the tip of a spike, what physicists call a throat, or composing part of a membrane wrapped around teacup-like handles. As you can see in this graphic, these scientists propose that our universe is constrained by brains or membranes in the 3rd dimension and the 7th dimension. When I published my book in 2006, did I know that string theory proposes this? I did not. Still, there seems to be another very interesting parallel here between my proposal that our universe is locked in at a position within the 7th dimension and the string theory idea that our universe is constrained by a 7-dimensional brain. My goal since the day I launched this project has been to continue to document interesting connections between leading-edge science and my approach to visualizing the dimensions, and I believe we're looking at a particularly useful one here. The word multiverse has a number of different meanings for different people, so there are some possibilities for confusion. As you'll see in the Wikipedia article on this topic, physicist Max Tegmark has proposed that there are 4 different levels of multiverse. Let's talk about each of these levels, beginning with level 1. Remember the cosmological horizon? It gives us a way of seeing that each of us is at the center of our own version of the observable universe, and that if we were on a planet billions of light years from here, we would still see ourselves to be at the very center of a different but essentially similar cosmological horizon. Those two would overlap much like a space-time Venn diagram. But what if an observer were so far away that their cosmological horizon didn't overlap with ours at all? In a level 1 multiverse, space-time is perfectly flat. On that flat sheet of space-time, there are an infinite number of self-contained universes, all with the same physical laws and constants. Almost all will differ from our own universe. However, because there are infinitely many, there will eventually be similar and even identical configurations. Even though this version of the multiverse has many supporters, particularly since it doesn't require the existence of any extra dimensions, I have to say that this one feels extremely unlikely to me. Max Tegmark estimates that within a level 1 multiverse, an identical volume to ours should be about 10 to the power of 10 to the power of 115 meters away from us. If a universe identical to ours is that far away, then how far away is the universe where I got up 5 minutes earlier this morning? And how far away from that one is the one where I got up 4 minutes and 59 seconds earlier? I would say it's easy to see why some people who are taught this version of the multiverse dismiss it as being ridiculously extravagant. With my project, I propose that the cosmological horizon is the space-time equivalent of the 3D horizon we see around us when we're in the middle of the ocean. It's the same in every direction because of an underlying curvature. Topologically speaking, if we think of our 4D space-time as a flat plane, or the surface of the ocean as a flat plane, where is the curvature? In either case, I would say it's in the next dimension up. So our observable 4D universe is really on the surface of a 5D hypersphere, which means that if Tegmark's calculation is correct, we have a measurement of the circumference of that hypersphere. Just as we could travel east on the surface of the Earth and eventually end up back where we started, this would indicate that if we traveled 10 to the power of 10 to the power of 115 meters, we would traverse the surface of the 5D hypersphere and end up at the same place we are right now. It also means that if I had adjusted my angle ever so slightly, I could have ended up in the universe that is really nearby ours in the 5th dimension, where I got up 5 minutes earlier this morning. But to be clear, my interpretation invokes extra dimensions, while the level 1 multiverse Tegmark is describing does not. Let's look at level 2. This is universes with different physical constants. In this version, the multiverse as a whole is stretching and will continue doing so forever. But some regions of space stop stretching and form distinct bubbles, like gas pockets in a loaf of rising bread. Such bubbles are embryonic level 1 multiverses. With my project, I've referred to this as the multiverse landscape and placed it in the 7th dimension and above depending upon the context of the discussion. But within Tegmark's classification system, his level 2 multiverse, like the level 1, does not require the existence of extra dimensions and is still on an infinitely flat expanse of spacetime. Here's level 3, the many worlds interpretation of quantum mechanics. Hugh Everett III's theory of the universal wave function, commonly known as the many worlds interpretation, tells us that observation causes one universe out of many to be selected, but the others continue on, just as real as the one we're in. Tegmark argues that a level 3 multiverse does not contain more possibilities than a level 1 or 2 multiverse. In effect, all the different worlds created by splits in a level 3 multiverse with the same physical constants can be found in some Hubble volume in a level 1 multiverse. Tegmark writes that the only difference between level 1 and level 3 is where your doppelgangers reside. In level 1, they live elsewhere in good old 3-dimensional space. In level 3, they live on another quantum branch in infinite dimensional Hilbert space. Similarly, all level 2 bubble universes with different physical constants can in effect be found as worlds created by splits at the moment of spontaneous symmetry breaking in a level 3 multiverse. Okay, at last we get to extra dimensions, even if they're infinite within Tegmark's classification system. With my project, I've suggested that these other universes resulting from different physical constants are at different positions within the multiverse landscape of the 7th and 8th dimension, and that having arrived at any particular location within that landscape, there is a potential for there to be a wave function of possible states, in other words, a set of parallel universes for the resulting universe within the 1st through 6th dimension. Now let's look at level 4. This is the ultimate ensemble hypothesis of Tegmark himself. This level considers equally real all universes that can be described by different mathematical structures. Tegmark argues that this implies that any conceivable parallel universe theory can be described at level 4 and subsumes all other ensembles, therefore bringing closure to the hierarchy of multiverses, and there cannot be, say, a level 5. Ultimate ensemble certainly works as a description of the 10th dimension within my approach to visualizing the dimensions, and I've been saying that to avoid confusion it's better not to call this overarching concept a multiverse, but rather the omniverse. This helps to keep it separate in our minds from the parallel universes of our own universe, which is Tegmark's level 1, which I've also referred to as our universe's phase space, and the multiverse landscape of possible universes, Tegmark's level 2 and or 3. On top of that, I have added the 9th dimension, which encompasses the dimensions below but moves beyond any physical expressions and into patterns of information only, and by then we are arriving at what Tegmark calls level 4. The omniverse then becomes either the 9th dimension in its entirety or the 10th dimension in its unobserved state, a single point representing the ultimate ensemble of all possible patterns and shapes, ready to be created through symmetry breaking to spill us back into the realities of the dimensions below. So, what is unique about the 7th dimension? Our universe never wanders off into the other different initial conditions universes as we observe the quantum wave function of possible outcomes for our universe, because it is constrained by its position, or a D7 brane as we saw in the string theory graphic we looked at previously, within the 7th dimension. Moving to another position within the 7th dimension and above precipitates a completely different universe with different basic physical laws. And for that universe, its expressions in the lower dimensions will be just as real as our own, and just as locked in by their position within the 7th dimension and above as our own universe is. As I've cautioned people from the outset of this project, my new way of thinking about time and space is not the explanation for string theory, it's just an innovative way to visualize 10 spatial dimensions, something that most people would have said was impossible to do. I've always remarked, though, that I find it interesting to see how many different spiritual and metaphysical systems have also placed a heavy significance on the number 7. So much so that one of the 26 songs I've attached to this project is called 7 Levels. Here's a link to one of the videos for that song. Let me close with this thought. If information equals reality, then absolutely everything about our reality can be thought of as patterns and shapes within the information that is the fabric of quantum indeterminacy, or Tegmark's ultimate ensemble. Subatomic particles, fractals, life, consciousness, and our observed universe are all structures that result from these underlying patterns that reside in that place where the distinction between past, present, and future is meaningless. Our own observed reality is being created at the fifth dimension, so anything beyond that becomes a part of the "you can't get there from here" list, unless we can someday navigate within those extra dimensions beyond the fifth. And as we get closer to 10, we are now starting to move away from the reality side of the equation and more towards the information side. We'll continue this exploration next time with imagining the eighth dimension. Imagining the eighth dimension. As we continue to add dimensions, the orthogonal hypercube projections that we're looking at here with each new dimension become increasingly ornate and, dare I say it, more Mandela-like. Another eight-dimensional shape that we've looked at with this project is Garrett Lisi's E8 rotation. Lisi created a huge stir in the physics world with a new proposal for what he calls an exceptionally simple theory of everything that uses E8, a complex eight-dimensional pattern with 248 points. As visually appealing as this shape might be, its implications are startling. Lisi has demonstrated that there is a way to place the various forces and elementary particles, including their possible quantum spin values, on E8's 248 points. Rotating Lisi's model in various ways reveals the explanation for a variety of interactions, some of which, like the clustering of quarks into families of 3, are natural outcomes from this structure. Some points in his model are currently occupied by particles which have been theorized but which have yet to be seen, and there is hope that the Large Hadron Collider in Switzerland may someday reveal some of those particles. Whether Garrett Lisi's theory proves the existence of higher dimensions or not is open to interpretation. Lisi himself says this geometric pattern, although it is based upon an eight-dimensional construct, could be fully realized within our 4D spacetime without requiring additional dimensions. On the other hand, in a New Scientist magazine article, string theorist Sabine Hossenfelder of the Perimeter Institute for Theoretical Physics points out that this could be complementary to string theory, which she says also uses E8 to describe the Calabi-Yau manifold, the extra-dimensional shape that string theorists say our universe is derived from. Lisi also acknowledges that this is not a finished theory but a work in progress, and that there are still some deficiencies in his model that need further refinement. For me, this dimensional connection is fascinating because with this project I've insisted that you can't have any physical expressions of matter in anything beyond the eighth dimension. A commonly asked question about this project is, if our universe and every other universe can be thought of as points or perhaps positions within a multiverse landscape, and in this way of visualizing the dimensions we get to that landscape by the time we're in the seventh dimension, then why do we need to think about any more dimensions beyond that? To my way of thinking, you can express the same concern about every definition of every single dimension, and the arguments have to keep coming back to, what are we missing within this current dimension? For instance, people say that the third spatial dimension is really all you need because no matter what other universe you imagine, it should have a third-dimensional expression. Or there are people who say all we need is space-time, because by the time you have the third dimension plus time, which gives the third dimension a way to change from state to state, then you can imagine every single possible universe strung end to end within infinite space-time. And because that string of all possible states is infinite, you will eventually get to every possible universe. Or you can have people who say space-time plus its probabilistic outcomes, whichever its many worlds interpretation says are orthogonal or at right angles to space-time, leading to my conclusion that these branches are in the fifth dimension, gives you everything you need to imagine every possible universe. From there, I've proposed that the branches for our universe, which no amount of chance or choice will allow us to select, like the branches where dinosaurs never became extinct, or the ones where I died in a car accident last year, are in the sixth dimension. And this uses the same logical reasoning that defines any spatial dimension. There always needs to be a new degree of freedom added for us to be able to call what we're talking about a new dimension. And the new dimension allows us to get to something that was unavailable from the previous dimensions. Likewise, I propose that those other universes with different basic physical laws are located in other positions within the seventh dimension and above, and this is why our universe, constrained at its position within the multiverse landscape, never wanders off into one of those other universes. So this is the question: why isn't the seventh dimension as far as we need to go? We have to continue with the logic we've used from the outset. Imagine a point of infinite size in the sixth dimension, and it's much the same as imagining the indeterminate point we started from with our thought experiment. The point encompasses the whole dimension. If we can think of a different point that is not subsumed by that first point, then the point-line-plane postulate tells us we found a way to get to the next dimension up. Those 2 points define a line in the seventh dimension. What if the second point we just imagined represents a universe where the strength of gravity is different from ours? Then the line that passes through those 2 points is like a one-dimensional line, and that line extends through all possible values for gravity. Different positions on that line would include impossible universes, which could not have come into existence because the strength of gravity was above or below a certain threshold needed to allow a physical universe to express itself. And such imaginary universes might be at many places along the line, interspersed with universes that were able to cohere into more organized states. What about a universe with a different value for the speed of light, or whatever physical constant you care to imagine? That's not on the line we just drew. We could erase the other point we drew, then place a new point for a universe with a different speed of light, and the new line that passes through those 2 points would be all possible realities resulting from different values for the speed of light. But what if I want to consider both lines simultaneously? It can't be done without entering the next dimension up, the eighth dimension. So with the logic of the point-line-plane postulate, we have a way of thinking of the eighth dimension as being like a plane, and our universe can be viewed as a point in the eighth dimension with those 2 lines or any other lines representing the other different initial conditions universes passing through our point within that plane. Remember this, with the point-line-plane postulate, the point you start from is in dimension x, the line to a different point is in dimension x plus 1, and the plane defined by a third point not on that line is in dimension x plus 2. Having worked through those 3 dimensions, nothing moves or changes about the first point. We're just adding dimensions that allow us to view that starting point from different perspectives. Thinking of our universe as a largest possible point encompassing the phase space of the 6th dimension, then, doesn't mean that we can't view the unchanging point from the widening perspective of the 7th or 8th dimension. Quite the contrary, this logic is the accepted approach to visualizing spatial dimensions. Likewise, the idealized shapes we've started each of these entries with, like the octaract at the start of this entry, have an underlying symmetry, where each of the points are equidistant to their adjacent ones in the same way that the adjacent points of a 3D cube are equidistant when viewed within the 3rd dimension. This means that the 8D octaract, like any of the other hypercube shapes, can be placed within a hypersphere with the same number of dimensions, and the other points of the hypercube are pushed apart from the center of the hypersphere symmetrically. The point of indeterminate size can become a sphere occupying as little or as much of the dimension it's placed within. At its largest possible expression, this point becomes a finite but unbounded hypersphere, occupying the entire phase space of the dimension it's within. The rotating shapes we're looking at now are known as the Platonic solids. Pictured here are the tetrahedron, the cube or hexahedron, the octahedron, the dodecahedron, and the icosahedron. Do you see how we can apply this same idea of symmetric points pushed out from a central position? This even includes shapes like the nested tetrahedra we see here on the left, which can be used to create the dodecahedron on the right. Speaking of phase space, here's a link now to a recent New Scientist article about a new paper published by physicist Lee Smolin and others at archive.org, proposing that all possible universes could be contained within an 8-dimensional phase space. To follow the logic we've been pursuing here, the 6-dimensional phase space for our own universe, or any specific universe with blocked-in physical laws, would be a subset of an 8-dimensional phase space that encompasses all possible universes. Likewise, it's worth noting that Everett didn't limit his theory of the universal wave function to just our unique universe. So while the phase space of a unique, different initial conditions universe such as ours could be encompassed within the 6th dimension, the logic we followed here shows us that Everett's theory ultimately should be considered from the phase space of the 8th dimension to include the wave function of all those other possible universes. So what's beyond the 8th dimension? The simplest way to take our thought experiment to the next dimension up now is to ask this: how would you jump from the universe with a different value for gravity to the universe with the different speed of light without passing through the intermediate possibilities? To get to that additional degree of freedom, you need the next dimension up. For our 2D Flatlander ant, that was the 3rd dimension. For our fly in the 5th dimensional garden hose analogy, that freedom to flit from location to location was in the 6th dimension. And for all those different universes considered from the 8th dimension, where do you think we'd achieve this additional degree of freedom? We'll talk about that next time with Imagining the 9th Dimension. Imagining the 9th dimension. I've been saying that the 8th dimension is as far as you need to go for any expressions of matter, while the 9th can only contain information or meme patterns, preferences for one kind of reality over another. How could I arrive at such an ambitious statement? With my Imagining the 10th Dimension project, I begin by saying that a point indicates a position in a system. In Imagining the 6th Dimension, I mentioned that thinking about the set of all possible states for our unique universe would be thinking about our universe's phase space. In fact, that's the definition of phase space, a space in which all possible states of a system are represented. I believe there's a way to apply this thinking to every single dimension. In a sense, a dimension, when considered as a set of all possible states for that dimension, becomes a finite but unbounded hypersphere. And that hypersphere becomes a point in the next dimension up. Let's go back and see how that logic holds up. If I'm on a boat in the middle of the ocean, I can see a horizon that appears to be the same in every direction. From this I can deduce that there is a slight curvature to the surface of the ocean, which is, topologically speaking, a 2D plane, and understand that I'm really on a 3D sphere. From the 2D topological perspective, I could head in a specific direction forever, giving me the impression that I was on an infinitely flat surface. But with the added curvature of the 3rd dimension, we can see how apparently infinite can be equated with finite but unbounded. With the knowledge that it takes a certain amount of time for light to reach our eyes, we realize that what we're seeing around us is not space, but space-time. And that, as counterintuitive as this may seem at first, it's actually impossible for us to see 3D space. We can imagine and use the logic of 3D shapes, but we can only see them from our moving position within 4D space-time. From our position within 4D space-time, we look out to the furthest reaches and see a cosmological horizon which is the same in all directions. From this, we can deduce that there is a slight curvature to space-time, and that we're really a point moving on the surface of a 5D hypersphere. There are many other indications that our reality comes from the fifth dimension. Back in 1921, Einstein accepted this idea as proposed by Kaluza. Holographic universe theories propose that we are an interference pattern projected from the fifth dimension or from the edge of the universe, but I disagree with those who say that this edge is far, far away. Think of it like this: the third dimension is at the edge of the second dimension no matter where our imaginary 2D flatlanders are located. In the same way, this edge they speak about in holographic universe theories as being at an additional right angle to our space-time reality is not far away. It's right here in the next dimension up, no matter where we are within our space-time reality. And Hugh Everett, even though he didn't propose extra dimensions with his many worlds interpretation, did propose that the branching universes derived from quantum mechanics occur within a space which is orthogonal or at right angles to space-time. Some quantum physicists are fond of saying that extremely unlikely events such as one of us suddenly disappearing from here and reappearing on the moon are allowable within the quantum wave function, but they are so unlikely that they would take longer than the life of the universe to occur. Likewise, Everett talked about how there are branching tree-like structures which are causally connected, and he even allowed for the possibility that some of those branches might fuse back together further down the causal chain. But he was very clear that causality could never be violated. So the universe where dinosaurs never became extinct, or JFK was never murdered, or where I died in a car crash last year, would exist within the universal wave function as described by the Schrödinger equation. But they are now inaccessible from the universe we are currently observing. Those other universes, in a manner of speaking, are beyond the horizon of our 5D probability space, which leads me to conclude that we are a 5D point moving on the surface of a 6D hypersphere. This sixth-dimensional phase space, as some have called it, includes all possible versions of our universe from its beginning to its end. But within that phase space, we never wander off into one of the other universes with different physical laws, because those are in effect beyond the horizon of our universe's phase space. And from this we can deduce that the system representing our universe as a timeless whole is a point on a 7D hypersphere. From here we are beginning to move into discussions of information flow rather than physical realities, but we're not all the way there yet. In his book Just 6 Numbers, Sir Martin Rees tells us that we only need to define 6 deep forces to describe our unique universe. Adjusting any one of those parameters by surprisingly small amounts would cause our universe to fall apart as the laws of physics break down. So if our unique universe is located at a position within the multiverse landscape, or constrained by a D7 brane, as some string theorists have suggested, then are we moving, or are we stationary on the surface of this 7D hypersphere? There has been some evidence that the basic physical laws of our universe may have been slightly different at the earliest history of our universe, which would indicate that perhaps we have changed our 7D position slightly, according to the logic we're pursuing here. But the idea that there is a certain natural selection occurring at the 7th dimension and beyond also makes sense. If we move too far away from our position, the incredibly delicate balance of forces that allow our universe to exist would collapse. So at nearby positions within this multiverse landscape, there might not be universes that cohere into any meaningful structures. But further away, another universe completely different from ours could be assembled with its own unique set of intricately connected physical laws and its own unique expression within the 6th dimension and below. We also talked last entry about how we can imagine a data set of universes within the 7th dimension, which would then require the beyond the horizon additional degree of freedom of the 8th dimension for us to be able to simultaneously consider other data sets not included within the 7th dimensional one. But to be clear, those data sets could be interchangeable. So this is more of a question of reference frames than it is of some data not being part of the 7th dimension. In that sense, the 7th dimension harkens back to the garden hose analogy used by string theorists. It's useful to imagine that the 7th dimension looks like a straight line. But when we move closer, we can see the dimension has the potential for additional twists and turns that are inside the rolled-up tube that is, topologically speaking, the plane of the 8th dimension. Now we're looking at an animation showing vibrating Calabi-Yau manifolds. We looked at this before in an entry called "Will the LHC Reveal Extra Dimensions?" With this project, I'm proposing that the 8th dimension would encompass every possible physical expression of every possible universe. What's beyond the horizon of the 8D construct we've just envisioned? String theorists who talk about there being 10 to the power of 500 possible universes are really describing the different possible shapes the extra dimensions could take. In The Hidden Reality, Brian Greene uses the image we're looking at here to picture the terrain of possible extra-dimensional shapes. He calls this terrain the landscape multiverse, as opposed to the brain multiverse, the quilted multiverse, and so on, and describes how quantum tunnelings through this mountainous string landscape realize every possible form for the extra dimensions in one or another bubble universe. To tie this idea to my approach to visualizing the extra dimensions, the topological plane of this landscape is the 8th dimension, and the additional degree of freedom allowing this tunneling to occur would be in the 9th dimension. So here we are in the 9th dimension. Now we really are into the realm of organizing patterns, or big picture memes as I've called them in my book, where we are finally fully into the information side of the information equals reality equation. What caused our particular universe to be selected from out of the sea of potential patterns that roil and froth like quantum foam at the 9th dimension? Back in July 2008, we talked in this blog about Michael Shermer, who's the well-known publisher of Skeptic magazine. Michael's goal has been to poke holes in the questionable claims of fringe science, the paranormal, and a wide range of other areas that he has targeted with his razor-sharp debunking skills. This is why I found it quite marvelous when I picked up an issue of Scientific American back then and found that Mr. Shermer's regular column that month was entitled "Sacred Science: Can Emergence Break the Spell of Reductionism and Put Spirituality Back into Nature?" Mr. Shermer's article is about a fellow who comes from my neighboring province of Alberta, Canada, Stuart Kauffman, founding director of the Institute for Biocomplexity and Informatics at the University of Calgary, who has written a book called Reinventing the Sacred. To quote from Michael Shermer's article about the book, Kauffman reverses the reductionists' causal arrow with a comprehensive theory of emergence and self-organization that he says breaks no laws of physics and yet cannot be explained by them. God is our chosen name for the ceaseless creativity in the natural universe, biosphere, and human cultures, Kauffman declares. By the time we are thinking about the 9th dimension as selection patterns that represent a generalized preference for one kind of universe over another, I believe we're in the same intellectual neighborhood as the God 2.0 concept. And I think Michael Shermer, famed atheist and skeptic, got it right when he concluded his article saying that Stuart Kauffman's God 2.0 is a deity worthy of worship. Why do I say this? Because by now we're talking about labels. A rose by any other name would smell as sweet. Whether you want to call these selection patterns that caused our universe to be selected from out of this sea of potential information patterns God, or some other less emotionally charged name, doesn't change the 9th dimensional reality that we're describing here. As I say in the last verse of my song, The Unseen Eye, now the universe of all universes, if the truth be known, is an awful bore viewed as a whole. But just a tiny shard, viewed from any angle, reveals complexity. It reveals such beauty, reveals a soul. So does it make a difference how we got to what we see? If it's really just coincidence, it's still a wondrous thing. If you are one of those persons who recoil at the use of words like God and soul, I apologize. This project is not an attempt to enforce a spiritual viewpoint onto the nature of reality, but it also tries to show that there are a great many possible connections between those different schools of thought. If you prefer physics over philosophy, so be it. That is one point of view. But likewise, if you prefer spirituality over science, I'm hoping that this project has given you some new food for thought for where the meeting ground between the two might reside. There are 26 songs I attached to this project, and I chose that number as a bit of an inside joke for fans of the history of string theory, and the very last one is called Thankful. Having a sense of wonder and gratitude for the immense processes which selected the universe we are in right here and right now is, to my way of thinking, a completely appropriate response. Are you enjoying the journey? My name is Rob Bryanton. Thanks for watching.